Happy New Year and Merry Christmas. Today with the team LRR, Live, Racel, and Raiza, we will discuss what liberation of geometry means. We will describe liberation of geometry in terms of the development of non-Euclidean geometry. How was geometry liberated in connection to the mathematician or to the people behind, and its implication to the extension of Euclidean geometry. What is liberation of geometry? So, first, it is a noun. As a noun, liberation is the act of setting someone free from imprisonment, slavery, or oppression. So, it means release or freedom from limits of thought. But how about liberation of geometry? So, liberation here is also a noun. And of geometry is a prepositional phrase used as adjective modifying liberation. So generally speaking, it is freedom of geometry. It was 300 BC, a 30-year-old Euclid published his compilation of books called Elements. This contains 13 books, where book 1 contains 23 definitions, 5 postulates, with 5 common notions and 48 propositions. Liberation of geometry starts with the curiosity of whether fifth postulate is a theorem or not. So we call this phase 1 as the investigation phase of the fifth postulate. And the fifth postulate states that if a straight line falling on two straight lines makes the interior angles on the same side less than the two right angles, the two straight lines, if produced indefinitely, meet on that side on which are the angles less than the two right angles. Meaning, if we have line L intersected by two straight lines, line M and line K, where the sum of the two same side interior angles is less than 180 degrees, then at some point the extended two lines M and K will meet. Ito yun, no? Ito yun, no? This fifth postulate is related to definition 23. Sabi ng definition 23 ni Euclid, parallel straight lines are straight lines which, being in the same plane and being produced indefinitely in both directions, do not meet one another in either direction. Kaya tinawag din itong parallel postulate, itong fifth postulate. However, focusing on the fifth postulate, nobody also knows whether Euclid sees it as a theorem kasi he avoided to use it for the first 28 propositions, and since there are 48 propositions, from 29 to 48 propositions na niya ginamit yung fifth postulate kasi it involves parallel lines. While countless mathematicians trying to prove the fifth postulate as a theorem, here comes Ptolemy in the 2nd century. He attempted na i-connect yung fifth sa 4 postulates but failed according to Proclus in the 5th century. Also, Proclus said the fifth postulate is a theorem, hindi siya postulate, because it is verbose, masyadong maraming words, and lack terseness and easy comprehensibility unlike the other 4. Also, it does not have the quality of self-evidence or ready acceptance demanded by the material axiomatics of the Greeks. The search is not over. Here comes 8th and 9th century, where the Arabs attempted to solve the mystery, and to do that, they need to translate Greek works to Arabic. But their attempt on proving the fifth postulate also failed. So the journey on the pursuit of fifth postulate investigation as the phase 1 has been revived, but a clearer version was provided by John Playfair in the early 18th century, so ang tagal. However, there are alternatives of parallel postulates sa ngayon that have been either proposed or tacitly assumed over the years. These are, una, meron talagang isang coplanar straight lines na always equidistant from each other. Yung second naman, kung may point na wala sa line L, then may line talagang dadaan sa point na parallel sa line L. Third, meron talagang pair of triangles that are similar pero not congruent. Not only triangles, but also polygons. And 6 more alternatives. But the clear version by John Playfair, this is known as the Playfair's form of the parallel postulate, states that through a point not on a line, so sa kanya pala yun, there is exactly one line parallel to the given line. On the same century, mathematician named Gerolamo Saccheri, he published Logica Demonstrativa, which arose to the new approach, the fifth postulate of Euclid, through reduction ad absurdum, in which showing the contradiction of the claim. Saccheri's effort to establish Euclid's parallel postulate by attempting to institute using a reductio ad absurdum was apparently the first time anyone had conceived the idea of studying the consequences of a denial of the famous postulate. So with this will lead to the second phase of liberation, which will be discussed by Ma'am Racel.
In continuation, Euclides ab omni nevo vendicatus, or in English translation, Euclid freed of every flaw. This was actually the logical study of the structure of Euclid's geometry with an emphasis of the place of the parallel postulate. So this little book was printed in Milan in year 1733, only a few months before the author's death. So with this, Saccheri tested the 28 propositions, and it is true. In this work, Saccheri accepted the first 28 propositions of Euclid's elements, which was, do not require the fifth postulate for their proof. Let us consider this isosceles birectangle, a quadrilateral ABDC in which AC is equal to BD and the angles at A and B are right angles. So Saccheri easily shows that the angles at C and D are equal to each other. So by drawing the diagonals AD and BC and using the simple congruence theorem, which are found among Euclid's first 28 propositions, Saccheri easily shows that the angles at C and D, as shown here in the presentation, are equal to each other. As a result, the two angles might both be right angles, both obtuse angles, or both acute angles. Saccheri named the three possibilities or three propositions as the hypothesis of right angle, the hypothesis of obtuse angle, and the hypothesis of the acute angle. Also, Saccheri presented the contradiction of Playfair's postulate. So now, the negation of Playfair's postulate has two parts. Through a point not on a line, so it's either there are no lines parallel to the given line, or there is more than one line parallel to the given line. Next, so Saccheri's work seemed to have been little regarded by his contemporaries and was soon forgotten. And it was not until 1889 that it was dramatically resurrected by his colleague Eugenio Beltrami. Saccheri's work has been translated into English and can easily be read by any student of elementary geometry. As with Saccheri, three hypotheses arise according to whether the fourth angle of the trirectangle is right, obtuse, or acute. So we have here Johann Heinrich Lambert. Lambert showed that in the three hypotheses, the sum of the angles of a triangle is equal to, greater than, or less than two right angles respectively. A third distinguished effort to establish Euclid's parallel postulate by the reductio ad absurdum method was essayed over a long period of years by the eminent French mathematician. So we have here Adrien Marie Legendre. So Legendre actually considered the three hypotheses according to whether the sum of the angles of some particular triangles is equal to, greater than or less than two right angles. Later, Legendre independently observed the fact already discovered by Lambert that under the third hypothesis, the deficiency of the sum of the angles of a triangle below two right angles is proportional to the area of the triangle. Legendre's last paper on parallels was published in year 1833, the year of his death also. He perhaps hold the record of or for persistence in attempting to prove the famous postulate. We saw that in spite considerable and prolonged efforts, Zachary, Lambert, and Legendre were unable to find a contradiction under hypothesis of the acute angle. These are the three people to suspect the independence of parallel postulate. So we have here Gauss, Bolyai, and Lobachevsky. Here comes the 19th century, where the peak of quest for the solution to the renowned problem regarding the proof of the fifth postulate of Euclid. A professor of mathematics at the Evangelical Reform College named Farkas Bolyai attempted all his life in attempting to prove. However, Farkas Bolyai always wanted his son to be a mathematician, and he brought him up with this in mind. Farkas believed that a sound mind could only achieve great things if it was in a sound, healthy body. So in his early years, most attention was paid to Janus' physical development. It was clear from early on, however, that Janus was an extremely bright and observant child. With Farkas' frustration to solve the quest of the fifth postulate, he was interested in the parallel axiom throughout his life. But his lack of success frustrated him to the extent that he warned his son Janus to give up its study on parallel postulate. Gauss and Farkas are friends that Farkas requested Gauss to be the teacher of Janus Bolyai, but Gauss rejected the idea. Janus completed 4-year engineering instead of 7 years. He was the top of the class of Royal Engineering College of Vienna. Even his mother died, Janus still graduated. Janus never drank coffee and described always with modesty of innocence that speaks 9 languages, with best swordmanship, violin, and dancing. Janus Bolyai began to follow the same path that his father undertaken his trying to replace Euclid's parallel axiom with another axiom which could be deduced from the others. In fact, he gave up this approach within a year, for still in 1820, as his notebooks now show, he began to develop the basic ideas of hyperbolic geometry. So on the 3rd November 1823, he wrote to his father that he had created another world out of nothing. On the same decade, Gauss and Lobachevsky separately put interest on the Euclid's fifth postulate, reviving the work of Zachary. They asked the question, can there be a system of plane geometry in which, through a point not on a line, there is more than one line parallel to the given line? These three mathematicians pointed out that there is another geometry where the 4 postulates hold true, but the 5th does not. Unlike for Euclidean geometry, the 5 postulates hold true. They call it hyperbolic geometry. However, Gauss called it non-Euclidean geometry and failed to publish anything of his work. Janus Bolyai, the son of mathematician Farkas Bolyai, who is a long-time close friend of Gauss, his work appeared as 26-page appendix to the first volume of his father's work. We have here Lobachevsky. He was actually the first to publish a systematic development of the parallel postulate. He studied at the University of Kazan. In the year 1829 to 1830, his earliest paper on non-Euclidean geometry was published in the Kazan Messenger. In the year 1840, a little book written in German, but in English, geometrical researches on the theory of parallels. On the year 1855, he published in French, Pangeometry, or in English, Pangeometry. All of them came to the same surprising conclusion. If the parallel postulate is replaced by part 2 of its negation in the Euclid's postulates, the resulting system contains no contradictions. That settled, once and for all, the 2,000-year-old question about Euclid's fifth postulate. The parallel postulate cannot be proven from the other four postulates of Euclid's geometry. This is the period where geometry was liberated from 2 or 3-dimensional concept to another dimension. So Eugenio, Arthur, Felix, Henry, and others, they actually furnish consistency proof of the hypothesis of the acute angle. So the method was to set up a model of a new geometry within Euclidean geometry, so that the abstract development of the hypothesis of the acute angle would be given a representation in the part of the Euclidean space. Any inconsistency of the non-Euclidean geometry is an inconsistency also in the Euclidean geometry. So Lobachevskian non-Euclidean geometry is consistent if Euclidean geometry is consistent. Another mathematician is also interested to continue the work of Zacharias negation, Bernard Riemann. Also asked, can there be a system of plane geometry in which, through a point not on a line, there are no parallels to the given line? So this was actually the question of Riemann. So Riemann observed that the extended continuously did not mean infinitely long. Say, for example, an arc of a circle can be extended indefinitely but its length is finite. Sabi niya, a straight line of finite length can be extended continuously without bounds, but all straight lines are of the same length. So Riemann discussed the concepts of boundlessness and infiniteness. So he published Riemann geometry in the year 1854.
To continue, in the visualization of the Riemannian geometry, lines here refer to the great circles, which is the largest circle that divides the sphere into two equal parts, while the shortest path between the 2 points or any locations is an arc of a great circle containing on those points. And any great circles, as you can see, the lines intersect, thus these lines are not parallel. In the middle of 19th century, there were 3 brands of geometry. These are Euclidean, Lobachevsky, hyperbolic, and Riemannian or elliptic geometry. Comparing these 3, Euclidean geometry states that through a point not on a line, there exists one parallel to the given line. In Lobachevsky, through a point not on a line, there are at least 2 parallel to the given line. Ibig sabihin, maraming parallel lines. While in Riemannian, there are no lines parallel to the line since the lines intersect. So walang parallel. Also, in Euclidean, 2 parallel lines are equidistant everywhere. In Lobachevsky, 2 parallel lines are taken to converge in one direction and diverge on the other, and parallel lines do not exist in Riemannian geometry. In terms of the sum of the angles in a triangle, it is exactly 180 degrees in Euclidean, while it is less than 180 degrees in Lobachevsky and more than 180 degrees in Riemannian geometry. Now, in relation to the ratio of circumference and diameter, it is exactly the value of pi in Euclidean. In Lobachevsky, it is greater than pi, and in Riemannian, it is less than the value of pi. Lastly, in Euclidean geometry, polygons are different areas, with different areas can be similar because not all similar triangles are congruent. But in Lobachevsky, similar polygons of different areas do not exist because similar polygons are congruent. Halimbawa, kung ang tao katabi mo, lalakad papalayo ng papalayo sa iyo, lumiliit ng lumiliit ang tingin mo sa kanya. So similar polygons are congruent. Now we have here the question, what does liberation of geometry mean? We can say that it is a freedom form of thinking that geometry is not only all about two-dimensional, but can be extended and can be advanced to n-dimensional possibilities. Whereas geometry of Euclid is not false nor wrong, it is true and right, but the extension on the fifth postulate has been liberated. Hence, liberation of geometry from the discoveries of Lobachevsky and Riemannian geometries give ways for various inventions of new and interesting geometries. Halimbawa, kay Einstein, ginamit niya ang idea ng Riemannian geometry in his study of general theory of relativity to describe physical space. At ang isang study, which conducted in 1947 of visual space, described using the Lobachevsky geometry. So certainly, the liberating discovery of Lobachevsky and Riemannian non-Euclidean geometries ranks as one of the great moments in mathematics. Now the question is, which is the true geometry? Which is the best geometry? Well, it is not about what is true or what is best. It is about which geometry works for you. So kunyari, if you're a builder, a surveyor, or a carpenter, then Euclidean geometry works best. If you're a theoretical physicist, then you can use Lobachevsky geometry. Kung ikaw naman ay isang astronomer studying distant galaxies, then Riemannian geometry is best for you. To wrap it up, the liberation of geometry started with the fifth postulate or the parallel postulate of Euclid. For more than 2,000 years, most of mathematicians believed that the fifth postulate is a theorem, and that many mathematicians attempted to prove it, but turned out to be flawed. It started with Ptolemy in the 2nd century, then Proclus in the 5th century, followed by the Arab scholars in the 8th and 9th century, where they translated classical Greek works including Euclidean element into Arabic. Then they tried to prove the parallel postulate, one of which is Nasir ed-Din. After the translation, another mathematician named John Wallis became interested in proving the postulate. Yet, bigo pa rin silang i-prove ito. In 18th century, John Playfair contributed his proposed substitute statement of the parallel postulate, which became so well known in many geometry books of today. Earlier in 18th century, Girolamo Zaccheri come up with its new approach to the fifth postulate by the use of negation and find contradiction. Out of all his researches, he was able to publish his book Euclides ab omni naivo vindicatis, or Euclid freed of every flaw. Although did not find one, through his works, another mathematician, Johann Lampert, discovered the measurement of lengths regarding the obtuse and acute angle hypothesis, along with Adrien Marie Legendre, who were unable to find a contradiction under the hypothesis of acute angle. Then, here comes the three people to suspect the independence of parallel postulate, namely Carl Friedrich Gauss around 1810, in 1832, Janus Bolyai, who exclaimed that out of nothing I have created a strange new universe. And in 1829, Nikolai Lobachevsky was the first to publish the systematic development of non-Euclidean geometry. The three of them concluded that parallel postulate cannot be proven, which led them to the discovery of new plane geometry, the Lobachevsky or the hyperbolic geometry. Not too long, Eugenio Beltrami, Arthur Cayley, Felix Klein, Henry Poincare, and others provided the consistency proofs of acute angle. Lastly, it was George Friedrich Riemann in the 19th century who discovered the second Euclidean geometry, the elliptic or Riemannian geometry. So as you can see, the steeper the line of the graph, the longer waiting time that the new interest sparked. And after that, it was like a blazing fire, new inventions and discoveries arise. So much thanks for these excellent people who made great contributions for the development and liberation of geometry.